So now that we've looked at the characteristic equation generally, let's go ahead and solve a specific second order linear ODE with these constant coefficients. Depending on when you got this pre-work, there may be some differences in the layout here, and I'll note any changes as we need to, but this function should still be the same. So we're going to guess, let's go ahead and say that, guess y of t is equal to e to the rt, and then we'll take the successive derivatives of it. Then we'll go ahead and plug this in to the original ODE. So that gives us we can then factor out the e to the RTs. And then we make the conclusion that either e to the RT equals 0 by the zero product property, but that's not true, or r squared plus 5r plus 6 must equal 0. So this is that idea of the characteristic equation, and you could see that we are always going to end up with a polynomial. In this case, it would look like r squared plus 5r plus 6. I'd like you to, for the time being, to keep proposing the solution, keep factoring out the e to the RT, keep setting it equal to 0 and saying that won't work, and so we've set the characteristic equation equal to 0. Eventually, though, you'll just jump to giving the characteristic equation for the homogeneous linear ODE with these constant coefficients. So eventually you'll just skip to this step, but for the time being I want you to keep writing all these steps out until you understand them. So then once we've got the characteristic equation, we do all of our algebra techniques. So in this case it's a quadratic, so we've got lots of techniques for solving quadratics. We could factor it, we could try completing the square, we could try the quadratic formula. We're just trying to find the roots of this characteristic equation. But if this were a higher order, if this were a cubic, because we started with a third degree polynomial, or a third order ODE, or a fourth order ODE, we'd have higher order polynomials in our characteristic equation, and so we'd start pulling on all of our techniques from algebra in that case. Here we're pretty lucky in that we can factor this. This factors to be r plus 3 times r plus 2. And we get that r is equal to negative 3 or r is equal to negative 2. So that gives us two solutions. Two solutions to this differential equation are y of t is equal to e to the minus 3t and y of t is equal to e to the minus 2t. So you can check, and I strongly encourage you to verify that if you take this function, take two derivatives of it, plug it into the original ODE, I want you to verify that you get a true statement. And the same thing if we use e to this root of the characteristic equation times t. So I do want you to verify this. Let me just add that. You verify. Then we get to the point where we don't yet have enough theory to say why this is a solution. But we will, without proof, I'd like to tell you that the general solution to this ODE then is y of t equals c1 e to the minus 3t plus c2 e to the minus 2t. So again, we don't have the vocabulary to say what makes this our general solution, but this is the general solution to this differential equation, meaning all other solutions to this differential equation can be written in this format. And that's the theory that we're going to be developing with vector spaces as we go along. But for right now, I'll just have you take it sort of formally that we find in this case, two, and we'll use this vocabulary later, these two linearly independent solutions to this second order ODE. And then we can go ahead and construct our general solution as a linear combination of those two solutions here. So this is what we give as our general solution. And we'll develop this more in class. So last thing I'd like to do then, and again, your notes may be laid out slightly differently, and I have to change this to a 5 here. So we've got the same ODE as before, and then I give you an IVP with this with these two initial conditions. So here are those two initial conditions. This would be y of 0 equals 5, and you may be missing it. This should say y prime of 0 equals 0. And then we're going to go ahead and give that particular solution to this ODE. And then I want to discuss these time series and phase portraits. So from above, we said that the general solution was y of t equals c1 e to the minus 3t plus c2 e to the minus 2t. And we'll take this information and try to find our coefficients. Now, we know we will be able to find c1 and c2. How come? Well, because this second order linear ODE has coefficient functions that are all constant, the existence uniqueness theorem guarantees we will be able to solve for c1 and c2. Let's go ahead and plug in time equals 0 into this function and set it equal to 5. So we get 5 is equal to c1 plus c2, because the e to the minus 3t when t is 0 is just 1. And likewise, this factor is just 1 there. Then we take the derivative of our solution, our general solution, and the derivative of the general solution is minus 3 c1 e to the t minus 2 c2 e to the minus 2t. I dropped that minus 3. And then we can plug in the fact that y prime of 0 needs to be 0, so we get 0 equals negative 3 c1 minus 2 c2. And now we can go ahead and solve this system of equations right here for c1 and c2. I'm not scared as I go about trying to solve this system of equations. I know there will be a solution. How come? Because the existence uniqueness theorem guarantees there will be a solution to this. So if we take, let's take the second equation here, and if we solve that for c1, we would get 2c2 divided by negative 3 is equal to c1. And then if I plug that into the original equation, we'd have 2c2 over negative 3 plus c2. So plugging it into here, we can solve for c2. So this gives me 5 is equal to 1/3 c2, or 15 is equal to c2. Once I know what c2 is, I can go ahead and find c1. c1 is equal to 2 times 15 over negative 3. And let's see here, that gives us negative 10. Double check me. And so we can give the particular solution to this initial value problem, this second order initial value problem. The particular solution then is negative 10 e to the minus 3t plus 15 e to the minus 2t. And this is the particular solution. This was our general solution. Any solution was going to have this format, but this is the particular solution, and it's unique because of the existence uniqueness theorem that we saw on the first page that satisfies this IVP right here. And you can verify that if you plug in 0 for t here, sure enough, yes, by the way we got these values, you get 5. And if you take the derivative and you plug in 0 into the derivative, you'll see that you get 0 out. Okay. So the next thing I want to do, the very last thing, is I want to look at these two graphs. These are the time series and phase portraits. The phase portraits we're going to do more with as we go along, and I just want to start exposing you to these. And then for the time series, though, the way I want you to think about this is here I just have graphed several different solutions to the ODE. This is to this ODE up here that we solved above. And so based on your choice of initial conditions, each one of these curves that I'm sketching here is a solution to the ODE. But the one that I want to look at is the one that we just found. Here, this one, I'll do it in purple. I thought that was purple. It's looking like a blue, I guess. So this blue curve right here is the solution we found, and I just want to make sure you understand why that's so. So notice that here on the axis we have time. Here on the axis we have maybe displacement, however you want to think about this, the dependent variable. And then we can see that we were told that our initial position when time was 0 should be 5. Well, sure enough, if I go right here, there's the ordered pair 0, 5. That's that initial position that we were given. And we were told that our initial velocity, if we want to think about the first derivative as a velocity statement, here is it should be 0. And sure enough, I've got a horizontal tangent line there. And so this blue curve is the particular solution to the original differential equation that satisfies these two initial conditions. The last thing I want to comment on then is this phase portrait. And so this phase portrait is different than the phase portraits we looked at before because this is a second order differential equation. But here, and this is where you need to start getting to be more careful as a reader you can see that we've got on our x-axis, we've got y, that's our dependent variable, and then we've got y prime on what is usually the y-axis, or the dependent axis. So pay attention to these labeling of the axes, because it will greatly clarify the questions you might have. And then what we do is for any ordered pair on here, so for example let's just pick this ordered pair right here. This would be the ordered pair 4, 0. We're going to go look at our differential equation, y double prime plus 5, and then this coordinate corresponds to y prime, so we'll plug in 0. And we have plus 6y, and y is the first coordinate, so we have 6 times 4. It needs to equal 0, and so we get that y prime in this case is equal to negative 24. So here we have drawn here, it's very steep, a line with a little direction arrow, a direction line with a slope of negative 24. So it's looking vertical, but it's negative. And you can actually then infer, over here as well, you can kind of infer those direction lines based on that. So what we've done here is we've created a direction field where every marking corresponds to the slope of that marking corresponds to the value of the second derivative. That's second derivative at any point in there. And I just want to point this out to you then. What was our initial condition? Our initial condition was at time t equals 0, y is supposed to be 5. Well, right here, this is where y is 5. So this would correspond to the time t equals 0. So the point, we can imagine this point moving along through different time values. And so time shows up in this problem not on the axes, but we just, maybe as time progresses, maybe this is about where time t is equal to 1, and maybe this is about where time t is equal to 2. And as time progresses, we can then read off this graph the values of y, the values of y prime, and then also based on the direction slopes, the value of y double prime. So this is a phase portrait. It's going to take a little while to get comfortable with this, but I encourage you to start thinking about interacting with these. Like, there's nothing I can say other than get familiar with these phase portraits by plotting some points, deciding how they got these direction slopes, trying to determine what these solution curves, what they represent, and experiment with that. Currently, more importantly, I think, is to look at these time series and make sure that those make sense to you, where here we've plotted several different colored curves, each of which solves the original, is a solution to the original ODE, and then in this case we've specifically drawn our solution to the IVP with this blue curve, and you can see that we have the initial condition that we're supposed to have and the initial tangent line that we're supposed to have. So folks, that was a long sequence of videos. I hope this was helpful, and I will see you all in class. Thank you.